Hi everyone, welcome to this new video. Today I would like to talk about A-star algorithm. I would like to start with explaining what is the difference between A-star algorithm and Dijkstra's algorithm, since we've implemented Dijkstra's algorithm before. So the main difference is that in A-star algorithm, uh, we consider the distance between the current node and the final node, which is called heuristics. You know, in Dijkstra's, we base our decision on the distance between the current node and the starting node. But in A-star algorithm, we're gonna sum up distance between the current node and starting node and the heuristics, which is the distance between the current node and the final node. And like one question that may raise is that, like, how do you actually calculate the distance between the current node and the final node? That's a very good question. So it's basically heuristics is basically an educated guess. So there are a lot of algorithms out there that allow us to estimate this distance. Uh, they are called, like, there is, for example, Manhattan heuristics, and there is also Euclidean heuristics. You can Google it. There's a lot of information about them online. But in this, that's basically beyond the scope of this video. But in this tutorial, we're going to just assign a distance between the current node and the final node. So in the video that I attached the link of below, they literally measure the distance between current node and final node with a ruler, with a scale. So you know, we can just assign a value, but one thing to keep in mind is that the value that you assign needs to be admissible. That means that it needs to be lower than the actual value. So yeah, that's the background behind this video. So let's just dive right into it. So first of all, we're going to create an object, a class tree, which is gonna be very similar to Dijkstra's algorithm. But in addition, we're going to add a dictionary that's going to assign a heuristic value to each of the node. So for that, we're going to add j dict is equal to this, and then I'm gonna add self dot uh, heuristics is equal to j, right? And then we're gonna want to add a function that's going to assign the value to each node. So for that we're going to write def h self letter, so the node in question, and then the value of the heuristics. Okay, and self dot heuristics. So this is going to send us back here, right? So heuristics, and then letter is equal to h. So this is going to assign a value to the node in question. Okay, so we're done with the object, and what we're gonna do next is actually write down the function that's going, the actual A-star algorithm function. So def solve tree. As an argument, we're gonna add tree. Tree is going to be this object right here. Okay. And then, of course, as we did with Dijkstra's algorithm, start. We're going to start. We're going to ask the user what is going to be the initial node. And then the ending node, of course. Okay, let's see right there. And then we're gonna create a priority queue like we did with Dijkstra's priority queue. We're going to heapify As a reminder, heap queue function heapify is going to rearrange the list into a ascending order. Heap queue dot heapify pq. We're going to add visited nodes. Visited letters. And then, okay, we're going to add a while loop, which is gonna be the core of the function. So one thing that I did differently with this is that whenever a node that has a lower value distance wise is encountered, we're going to place it directly in the priority queue, as opposed to what we did in the previous video. That's going to make things easy. So this is going to make sense if you actually watch the video that I put in the description. So yeah, a false current node. So to initialize the while loop, I'm gonna start current node start and then current distance 0. That's just to initialize, they're not necessarily true. Current distance counter call -1. This is going to make sense once I write the while loop. False. Those are just initial parameters. So okay, let's write the while. Okay, there is still b the initial node, tree.heuristics start 0 and then start. So in this tuple we have three values. So here we have the heuristics value. So this is supposed to be the total distance between the current node and the final node. So since the distance between the current node and the starting node is 0, because we're starting with the starting node, we're not gonna, so the distance, we can compute that the distance between this node and the final node is just the heuristics, and then 0 is the current distance from the current node, which is 0, and start, that's the letter node. Okay, let's start writing the while loop. While a is not equal to true. Okay, right, is not equal to true. Alright, while a is not equal to true, we're going to visit all the nodes that our current node is attached to. So for that we're going to do for v I in tree.tree and node items. Okay, so it's going to visit all the nodes of the current nodes, and we're gonna be recording the key and the value, right? And then we're going to check if those nodes are actually in the priority queue, or we're going to check if those values have already been added to the priority queue previously. So we're gonna see for h, okay, h in PQ, PQ being the priority queue, counter plus is equal to 1. So this is going to record the index at which index in the priority index we're at in the priority queue, right? So it starts with -1. So the first index is going to be 0. So that makes sense. And then if we happen to have a node h2 that is equal to the node that we if we happen to encounter a node in the priority queue that is the same as the node that we're visiting, h2 is equal to v, then what we're gonna do is to try to compare the actual value, to compare the distance. Okay, we're going to compare the distance between this node and the current this node and the starting node, and see if the value that we got is actually smaller than what has already been recorded. This should make sense. He explains it very well in the video that I put in the description, but I'm gonna do h1. So h1 is going to be the value that's already been stored in the priority queue, greater than this sum right here, current distance plus I. This sum is going to be the distance, the current distance that we get, and of course v not in visited letters. We do not want to revisit letters that have already been worked on before. Then we're going to replace it in the priority queue. So this is where counter is becoming effective. Counter, pq counter is equal to 3.heuristics v plus current distance plus I. So that's gonna be the first value. As you may have noticed, it's gonna sum up heuristics and current distance. So it's gonna replace that first index by the total distance between the starting node and the final node, if we go through the current node that we're visiting, and then current and current distance plus I. So this is gonna be the distance between starting node and the node that we're visiting, and of course a letter. Okay, so either way, if we encountered a node that happen to be the same, we want to change added to true. Okay, and then we're gonna exit out of this loop, the first loop over here. And in case we haven't added anything, if added is not equal to true, right? If we haven't encountered a node that has not been added to priority queue before, that means that we haven't done anything to it yet. So we want to add this to the priority queue. pq plus is equal to 3.heuristics v plus current distance plus I, current distance plus I and v. Okay, this is pretty straightforward, the same as this right here. Okay, we're gonna reinitialize the counter back to -1, because we will have visited one node that's attached to the current node we're working on, and then added false. Okay, so that's the while loop, the for loop, sorry. And then once we're done visiting that one node, we're going to add it to the visited letters list. So we're gonna do visited letters is equal to plus equal to current node. Okay, so the current node, yeah. So at first the current node is start, but start right here. Okay, we're gonna see it's going to change. Visited nodes is equal to b, which is right here, but this is going to change in the next steps that I'm going to write. B is equal to heap q dot heap pop pq. Okay, this must be the most interesting part. The value that has the least distance is going to be popped out of the priority queue, and this is going to become our current node. But first of all, we're going to see if that node that we just removed from the list is going to be our final node. That's when you know you're going to stop the algorithm. So if b2, remember that 2 is going to be the letter, 2 is equal to AND, then a is equal to true. A equal true, that means that we're going to stop the loop. We can just put break. Alright. NUL is equal to B0. Okay, current node is equal to B2. Current distance is going to be B1. Alright, so current node is going to be B2, because B, we just extracted it from priority queue, and B2 is the letter and B1 is the distance. Okay, that's where we're at. And one thing to know is that if B happens to be the node, the final node, then it's not going to replace the current node by the current values. Okay, very important for next steps. And then we're going to work our way backward to retrace the path. Very similar to Dijkstra's algorithm, so I'm not going to explain anything here. We have B2. I'm not going to go into detail. Current distance is equal to B1. QQ is equal to false, and break 4 is equal to false. So very similar to previous algorithm. Well, QQ equal to true. For key value in 3.3 CL. Okay, items for J in visited nodes. So this is going to visit every node the current node is attached to. If you think about it, it's very similar to this, but in a reverse order. We're going to go backwards. So if cdd minus value is equal to J1 and J2 is equal to key, I'm gonna have print J2. So that right here is going to print the node, corresponding node. Then we're gonna replace CL by J2 and CDD is called J1. Break 4 is equal to true. Okay. We have replaced the value, and then if break 4 is equal to true. And I'm gonna break it. Okay, so if you find a value that's corresponding to the one that we're looking for, then it's going to get out of this for loop. Okay, so basically what this does is that we have a current value, right? And we're going to go through the list of the visited nodes, and okay, there's a value for each of the weights that one node is associated with, and we're going to subtract the weight from the current value, and if there is a corresponding value in the visited nodes that we have, then we're going to print the letter, and we have to make sure that the actual letter corresponds to the one that we're currently visiting. It's going to make sense if you watch the previous video. And then we have to reinitialize. Break 4 is equal to false if cl is equal to start. Right, if we reach the very first node, then we're gonna want to stop the algorithm, right? Else we're gonna keep it false. Right, okay. I want to return b1. b1 is the minimum distance, right? So there we have it. There we have, that's the algorithm. Actually test the algorithm with the graph that's in the video that I put in the description. So first of all, we're gonna create the tree object, t.attach. We're gonna attach first of all b, distance of 2, attach a that has a distance of 7, t.attach sb ab that has a distance of 3, okay, 3, b and d a distance of 4, okay. A and D, okay. t.attach A and D. It has a distance of 4 as well. B and H. B and H has a distance of 1. H and F. H and F has a distance of 3. D and F has a distance of 4. Okay. distance of 5, sorry. Okay. Alright, we're going to go the attach H and G, distance of 2. G, okay, G and E, distance of 2. Going to go back to S, C, distance of 3. C, L, distance of 4. L, J, distance of 4. L, I, distance of 4. Okay, CL has a distance of 2. Alright. L and I, distance 4. I, J, a distance of 6. I, okay, I, K, distance of 4. J, K, distance of 4, and finally K and E, distance of 5. Right, and now we're gonna assign the heuristics, very interesting part, because that's different from die-stress algorithm. So we're just gonna do T dot H. Okay, T dot H. Okay, let's send the letter S. 10. Those are just estimate distances that are mentioned in the video. T dot H, B, 7. T dot H, A, 9. Okay. T dot H, D here. Is going to be 8. Okay. T dot H, letter H, heuristic distance of 6. T dot H, F, there's a heuristic distance of 6. T dot H, G, heuristic distance of 3. H, E, heuristic distance, of course E, heuristic distance is 0 because that's the final node. T dot H, heuristic distance of K, going to be 3. T dot H, I, that's going to be 4. T dot H, J, going to be 4 as well. T dot H, L, going to be 6. T dot H, C, it's going to be 8. Okay, I hope we haven't forgotten anything. Okay, so we're going to run the algorithm to test it out. Okay, solve t, which is the tree that we just created. Initial node S, final node is going to be E. There you have it. That's the path that we're going to follow in reverse order. So we're going to end at E, go back to G, go back to H, B, S. That's the path, and the least distance is 7. There you have it. The algorithm works perfectly. Thank you for watching this video.